Good morning, everyone. So I will soon start sharing the screen and we can get going. Yeah, good morning. And this was the theorem which we were proving in the last class. So C is an irreducible closed set of recurrent states, and T is the entrance time into C. So since it is an irreducible closed set of recurrent states, we know that probability of entering that is also the probability of eventual absorption in C starting from an X in the state space. Then the first conclusion of the theorem is that rho sub C is equal to X if X belongs to C, and it is 0 if X is a recurrent state but does not belong to C. This is very obvious. And the second part of the result is that is rho C considered as a function on the set of all transient states. It satisfies this set of system of equations. This also we have proved last time. And the third conclusion, by the way, first two conclusions hold even if the set of transient states is not finite. If the S sub T is finite, then
have you studied the lecture just now?
Yeah, I'm just recalling that the statement of the theorem, which we had partly proved last time. First two parts we had proved. The third part also we had gone ahead with the proof to some extent. So if the set of transient states is finite, then we can say something more. Namely, if you consider this equation, this system of equations, this is precisely really the equation. And this says that rho sub C is the only solution to the system. So the advantage being, if one is able to solve this system of equations, knowing just the transition probability matrix, and if the S sub T happens to be finite, then one can conclude that function is precisely rho sub C. Okay, so all these things you might have copied it down last time itself.
Sir.
Yeah.
Sir.
Yes.
So have you started the lecture just now?
Yes, sir. I'm just
doing
a recap.
Okay. Okay, basically. Okay, so these are slides from last class. Okay.
Last class, yes. So I presume you would have copied down all these things. So part 1 is easy to see, and part 2 we had proved. Somebody's microphone is.
So what is the first slide of today's class?
Huh?
No. What is the first slide of today's class?
Meaning what? Today I just.
What is the first slide of today's class?
The theorem, statement of the theorem.
Okay.
I've shown last time. I'm doing a recap.
Okay. I got it. Okay.
So if you see these things, it should be familiar from your notes that you might have taken down last time. Okay, part 3. So first observation is that if you consider this function, X going to rho sub C of X as a function on the set of transient states, one knows that from the part 2 of the theorem, that is a solution for the system of equations, which we had noted, shown by this bullet. So this second part of the theorem implies that rho C is a solution for this system. Okay, and that happens even if the set of transient states is not finite. So now we will consider only X coming from the set of transient states. So we had seen in the last class, the first of all, Tc equal to 1 is just the term summation P xy, y varying over C. And P sub x of Tc equal to 2 turns out to be this. This we had proved last time. We had also observed that if you take P super 2, the superscript 2, x sub z, xz, sub xz, where both x and z happen to be transient states, then the intervening, that summation involved is also only through transient states. Remember that in general that will involve summation over y running over s. So all the recurrent states, I mean none of the recurrent states will occur in this summation because of this reason. And also by part 1. So similar conclusions you can sort of try first see for P super 3 and so on. All these things you can easily obtain by similar arguments. And I think this is where we had stopped last time. So the real first slide of today's class will be the next one. Okay. So let the cardinality of ST be finite. So there are only finitely many transient states. And let F be a function on S sub t satisfying the system of equations. Part 2 guarantees that there is at least one solution because rho sub c itself is a solution. Now, the idea of the proof is the following. I'll go back to that equation. Yeah. Look here. So we are assuming F is a solution for this. So F of x, I mean, this kind of argument you might see in many proofs concerning uniqueness in various contexts. F of x is equal to this. Now, this Fy can in turn be expressed in terms of this equation. Okay. So maybe in that case, you will have to use, I mean, introduce another index, subscript is z, and so on. Yeah, that is what we are going to do. Yeah. So using that equation twice, okay, the equation, the first time when we apply this, we get f of x is equal to this. This is just, I'm repeating the equation. Now one is expressing this Fy again in terms of that equation. So it is, when we do that, this is what we get. And observe, this term is precisely P sub x Tc equal to 1. And what we had seen last time, the second term is precisely P sub x Tc equal to 2. And what is left out here is summation over z varying over st, P super 2 xz applied to fz. Note it down if you want. Okay. The next step is combine these two. This is P sub x, T sub C less than or equal to 2. So that is what we are having. For any x in ST, instead of that Z, I am just writing again by Y. That is, here I am, if these two can be combined and called P sub x, TC less than or equal to 2, here instead of having Z, I will just replacing it by Y. That's all. Now iterate. The next step, you can replace for this Y in terms of the equation bullet. So doing it again and again. So in n steps, you will get f of x is equal to P sub x, Tc less than or equal to n, summation y varying over the transient states, P super n xy fy for every n and for every x in the set of transient states. So for any this thing y in ST, go through the theorem 4 is the previous theorem, which we had called as a general theorem. After looking at the birth death chains, we had a theorem, and that says is for any finite state space, the set of these things, there will be at least one recurrent state. During that proof, we had shown that for a transient state, this is what happens. Limit n going to infinity, P super n xy is 0. Proof of this did not really involve that state space is finite. Only when we summed over x, there we had used finiteness. The things involving this were in proving was that gxy converges for a transient state y. So we have this information from the proof of the previous theorem. Since S sub t is finite, the function f is bounded on S sub t. So since it is a finite set, we have the limit and the summation can be interchanged. So when you do that, this limit is equal to 0 for every y. But of course, this is bounded, so all these things can be justified. So this is equal to 0. So therefore, f of x, so that second term here goes to 0 as n goes to infinity, and that keeps on accumulating, and the limit that is precisely p sub x tc less than infinity. And which precisely is rho sub cx. So we have got any arbitrary solution f is exactly rho sub c on the set of transient states. So rho sub c is the probability of eventual absorption in C. So this completes the proof of the theorem. Of course, this theorem is useful when in the state space is finite and so on. For example, the gambler's ruin problem, to find the probability of the absorption at C, that is the probability of eventual ruin of the gambler, we did not use this method. So in such cases, in the birth-death chain and things like that, you have a very nice structure in the process itself. So it is better to use that to get some kind of a recursive relationship, which that's what we had got concerning that psi, or some kind of a functional equation for psi, which can be solved using certain boundary values. Please note it down. And this kind of using that equation and iterating that to prove uniqueness is somewhat of a common technique in many contexts to prove uniqueness of solutions for certain equations. You might encounter in other disciplines also. Please note it down. So we will look at one example. So let Xn be a Markov chain on a 7-point set. State space is yes, we are denoting it by 1, 2, 3, 4, 5, 6, 7. And the transition probability matrix is this 7 cross 7 matrix. Those of you who are taking down notes, please carefully take down this matrix, because, and then many things which we will be saying is sort of, you may have to stare at that matrix. Please note it down. So here, for example, this first row corresponds to from this initial state 1, I equal to 1, the probability of the chain going to the other states, various states in the state space in one step. For example, from 1 in one step, it can go to 1 itself, or it can go to 2. And similarly, if the initial state is 2, in one step, it can go to 1, 2, or 3. So here note that from state 1 to state 2, you can go in finite number of steps with positive probability, namely that the probability is at least half. And similarly, starting from state 2, you can go to state 1 in finite number of steps with the positive probability. That is at least 1/6. So states 1 and 2 communicate with each other. And similarly, you can see states 2 and 3 communicate with each other. And so on. So please note down the matrix carefully. Of course, this will be put up this afternoon. I mean, Moodle, this part of the. Okay, I am going to the next slide. So from the matrix, the following things are clear. 1 and 2 communicate with each other, we had just seen. And similarly, 2 and 3, 3 and 4, and 5 and 7. So 3 and 4, you can see. And similarly, 5. This is the 5th row. And from the state 5, in one step, it goes to 5 itself, or it can go to state 7, number 7. And similarly, from state 7, it can go to 5 in one step or stay in state 7 itself. So 5 and 7 communicate with each other. That is what. So which means from 1 to 4, you can go in finite number of steps with positive probability. Okay, what about state 6? I will go back to this thing again. If you start from state 6, in one step, either you can go to 1 or stay in 6 itself or go to 7. But from state 1, you cannot come to state 6. So note that from no state other than 6 itself, you can come to 6. The column vector corresponding to 6th column vector has got only one positive entry, and that corresponds to P66 itself. So from k equal to 6, there is no way, for k not equal to 6, from 1, 2, 3, 4, 5, or even 7, you cannot come to reach. See, from 5, if you have to come to 6, either you have to come from 5 directly in one step, or you have to go through some other steps. For example, from 5, you can go only to 7. All the other, these upward here are 0. From states 1 to 4, you cannot come to 5. So for example, this block, 4 by 4 block, that forms a transition probability matrix by itself. In this case, say for example, in this 7 cross 7 transition probability matrix, this forms a 4 by 4 block. All the things are here 0 and so on. And similarly, if you consider the 2 cross 2 matrix consisting of states 5 and 7 itself, that is a 2 cross 2 transition probability matrix. So in other words, the Markov chain restricted to C1 is by itself as a Markov chain and confined to this irreducible set, finite irreducible set, and also all the states, they are recurrent here. There. Note it down. So denote by C1, C sub 1, 1, 2, 3, 4, the first 4 states. And C2 is 5 and 7. So observe that from C1, no state outside C1 can be reached. So this C1 is a closed set. So it's also clear that the C1 is irreducible. So it is an irreducible closed set. Because C1, from 1 you can go to 4, from 3 you can go to 2, 3 you can go to 1, all these things with infinite number of steps with positive probability. And of course, since it is an irreducible closed set, this thing confined to the chain confined to C1 is a Markov chain with finite state space C1. And since all the states, that is a finite set, there exists by theorem 4 at least one recurrent state, and therefore the process itself on C1 is recurrent, which means all the states in C1 are recurrent. So C sub 1 is an irreducible closed set of recurrent states. Note it down. So all this information you can get from carefully observing the transition probability matrix. Of course, since it is a fairly small set, state space of order only 7, these things are easy to do, more or less visually, just staring at the transition probability. Okay. Similarly, C2 is also an irreducible closed set of recurrent states. So note that row 6, 6 is strictly less than 1. Because from 6, you can go to 1 and 7. But from there, you cannot come back to 6. So rho 6, 6 is necessarily less than 1. So it is a transient state. So therefore, S sub T, the set of transient states, is a singleton here, namely consisting only of 6, that element 6. C1 union C2 is S sub R, that is the set of all recurrent states for this Markov chain, which is the disjoint union of two irreducible closed sets of recurrent states, C1 and C2. So the probability of, if the Markov chain starts from the transient state 6, the probability of eventual absorption in the irreducible closed set of recurrent state C1, let us denote that by rho sub C1, and corresponding to absorption in C2, we can denote by rho sub C2. I'm going to the next slide. So for I equal to 1, 2, let F sub I denote the unique solution to the system of equations, this, which is guaranteed by the theorem. So this is the one corresponding to C sub 1, F1, F2 is corresponding to C sub 2, this equation. So by the theorem, we know that, rho sub Ci at X, this should be I, please. For I equal to 1 to 4. I think there should be an equality sign here. Sorry, there are two typos here. For I equal to 1, 2, rho sub Ci at 6 is Fi6.
Sir, can you once again go to the previous slide? The one before it? Okay.
Not it down.
No, the one before it. Just okay, yeah.
Note it down.
Yeah, it's fine. Yeah, it's fine. Okay, fine.
So there are two typos here. Here, this comma, please replace by equal to, and this 1 should be replaced by I. The subscript 1 is I, should be replaced by I. So since ST is just a singleton set, this summation will involve only one element, namely y equal to 6, and so on. So you can easily solve, and solving that, I leave it to you as an simple exercise to show that rho sub C1 of X is half. Oh, here again it should be C2. There are 3 typos. I was elated because this was the last slide for this thing. So quite a few typos in this slide. This should be I equal to 1, 2, and this is rho sub Ci at 6 equal to Fi6, and rho sub C1 6. Since rho sub C2 is also the same number, there was copying and pasting done while typing, but I forgot to replace this 1 by 2. Please correct it. This is rho sub C2 here. But however, please don't make such mistakes in your exams. You will be penalized. Fortunately, the teacher generally doesn't have to write the exam. So that is all for the midterm. So what we
So the midterm syllabus is up to this point, right?
Up to this point, yes. And at this part of
so the midterm syllabus is up to this point, right?
Yes, this midterm syllabus is up to this point. And this part of the thing will be put up in soon, in Moodle. And that I think that process I should correct.
So you will upload Markup chain 6, right?
That's why if the number is 6, I will upload.
Okay, so all these things will be in the lecture notes. Okay, fine.
But if you want to copy down, because usually copying and writing is perhaps one of the best ways to learn. And also the teacher feels happy that his effort is not really wasted. And that is all for today's class. The next class we will begin with stationary distributions.
So is today's class over?
Today's class is over, provided you give me permission to stop sharing, and then we can end the session.
So when is the next, when is the mid-sem?
Mid-semester exam, I think I had sent an email to you all, November 13th, 10:30 to 12:30.
Yeah, it's 13 November, I think.
Yes, 13th November, it is a Saturday.
Yeah, means it is 13 November, 10 to 30.
10:30 to 12:30.
Sir, I mean, I will be at CMI and maybe a couple of us might be at CMI on 13th November. So is it necessary that we actually scan and then submit on Moodle, or when if you write on paper, can we just leave it in your office or something?
I don't have any office in CMI. I am now.
Okay.
I am remote. I am a remote person. Okay, so you can submit on Moodle, but another thing is I will give you all one alternate this thing account I have created in Gmail for this purpose. That I will let you know. You can scan the thing and send it to that address if you want. The Moodle, the only thing is that since it has about 70 names.
Okay, but then sir, what is the Gmail address?
I will give it to you soon.
No, I have a question. So what is the Gmail address of the alternative account which you have?
What I will give it to you soon. Yes, about 2 weeks are there for the exam, right?
Okay. Okay.
Don't get very tense.
So do we need to send our solutions to? No. I am saying, do we need to submit both in Moodle and as well as to send it to you?
I'm giving you a choice. If sometimes the Moodle may not accept or whatever it is. Say, supposing Moodle, I think, has certain upper limit for the files, this thing, capacity, size, file size. So it may not accept.
Okay.
Or if you have.
But if the Moodle accepts, then no need to send it to the other mail.
I think certain things, I leave it to common sense. Okay. Don't get so much tense. When you get tense, I get tense. Okay. So don't make me tense.
So what will you start in the next class? What will you do in the next class?
Stationary distributions. Okay, I think I will stop sharing.
Stationary.
All right. So we will end the session now. And I observe only very few students are attending. What is the problem? I don't know whether I should report. Okay, of course, those things doesn't concern you. You people, I think, seem to be quite regular. But I mean, again and again, one only sees certain familiar names. and also the number of participants is in single digits. Okay, I will end the session now. Take care, then see you on Friday.